So hello everybody and welcome to the third part of the course on testing, which is a part of our total course on entire system, embedded system design, verification and test. And now as we are looking for the last few weeks, we are dealing with embedded system testing. So now also we have covered the first module on the testing part, which was on the basics, and after that we have started covering some very important topics which are more focused to embedded system based tests. Like in the last lecture, we have seen how basically high level or functional fault models are used for testing of complex embedded systems. What we are going to see today, we are going to see today that how you can access the points of testing in embedded codes. Let me make this story a little connected to the whatever we have learned in the first few preliminary lectures, that if you want to test a system, you have to first find out the vectors and then you have to apply them. For doing it, basically there is something called an ATE or some equipment from which you can apply the tests. But in case of embedded system design, we generally have a large number of ICs, or in other words they are called cores, which are in a bigger system. So it's something like a system of systems. Like in this a system of hardware modules. So there can be a larger module. Inside that module there can be small hardware modules which are fabricated in a chip. So we call that embedded cores. Why the concept has come? Basically the concept has come because one vendor cannot be expertise in manufacturing or designing all kinds of IP cores. Like one person can be more dedicated towards graphic processing, one can be more dedicated towards designing of processors, one vendor can be more expertise in design on chip memories and so forth. So what a person does, if you have to design an entire embedded system hardware, he will design some of the modules, and other modules he will procure directly from some vendor who is expert on that and put them together on a single die and give it to fabrication. Because embedded system hardware, when we say in that fashion, or a system of chips, or basically network on chip, it is not like that you buy individual discrete components and connect in a board. That will make things work, frequency will come down. Because we all know that whenever we have multiple systems on a PCB, the interconnecting wires etc. take the most amount of delay. So better with that we purchase all the cores. Cores means the hardware design or design in a hardware level. It can be at the register transfer level code, it can be at the gate level, or it can be even at the layout level. We purchase those codes and put it in the die according to the placement requirements, and then also we put our logic blocks whichever we have designed, and finally give the chip for manufacturing. So that is what is called the embedded system core based design. Now what happens, so if you have such a system, so in which case for some of the cores which I have designed, I have entire knowledge, I can put my DFT requirements, where to put scans etc., and I can make my life easy for testing. But think of the other cores which are purchased from other vendors. They may not be actually, in fact they are called IP cores, because nobody will tell you about the internal details of their design. They say that it's a processor, they will give me the processor, they will tell me that what are the test vectors required to test the processors, what are the routines etc. Rather than that, they will not give me any more details. So I cannot change it for most of the cases, I cannot put additional DFT, and but still with the existing test vectors which have been given to me by that vendor, I have to test it in entirety. Like so I have 4 modules. So let me assume that this is my entire die. So these are the two IP cores which I purchased from the market. Core means they are also simple hardware designs. They can be at the gate level, register transfer level, or it can be at the layout level. And 2 I design. These are my designs. So I design these 4 blocks in one die, and I send it for manufacturing. Now for this I have full control, I can put my DFT circuit etc. But for these blocks I do not have much information, only because they are IP cores which have been sold to me by the vendor. Why I am purchasing it? Because I do not have much expertise to design them. Better I purchase it and I concentrate on my design. But I have to design the entire embedded system hardware and sell it to the markets. And it is a very standard practice in current industry. It is just like software module, that some modules you develop and others you use library modules. But in case of software, basically there is more flexibility, but in hardware the flexibility is less, because once you fabricate it, the whole thing gets fabricated and you have to depend on the performance of not only on your own design but also for the other design. The rigidity is more in hardware, as we all know. Now secondly, nobody will tell you the internal details, but obviously you have to test them. So what these people will do, these IP vendors will do, they will, along with this IP cores, they will also give you the test patterns which is required to be tested. Again, and one more thing, basically they will also give, sometimes they call something called a wrapper. They give a wrapper, that means the way to access this IP blocks in test mode and normal mode. because that is the entire circuit given to you, because what I do, you can read about some other books also on test based hacking. So if there is lot of access given to this internal IP cores, but because for the course you have designed, I have full knowledge, but for the IP cores I have sold it to you to be using. I don't want you to back engineer it or reverse engineer it. So now what happens, if I give more access to the pins of the IP cores, I can do a reverse engineering and I can try to find out your design. So what they do, they give also a wrapper kind of an architecture over the IP cores, which tells you that these are the patterns to be applied, and you have to apply through the wrapper. They will make proper interconnection between the IP core and the external world, and there can also be a operating mode, normal operating mode, which is the normal function mode. So also that means they have a wrapper, so that it becomes a very encapsulated IP core, so that it functions in test mode, as well as you can test them with the vectors already provided by the vendor, but you do not get much insight into the design. So this is actually called core based embedded system design. Now the challenges remain that how do you test in entirety. Test pattern generation is very simple in this case. For this design I generate by my whole algorithm. For this IP cores, the test patterns are already given to me by the vendors. Now the problem is that I have to apply them. Why? Some picture I will show you, then again I will come back to the normal discussion like this. So there are maybe 4 internal logic blocks. Maybe this I have designed and this I have designed, and this one is actually IP and this one is IP. Now how do I apply test patterns? Because the number of input outputs may be very less. Maybe I can say that these are the IOs, these are the IOs, these are the IOs, but these are some of the internal pins which are not directly accessible, because they are 4 IP cores and they are the internal lines. So there should be some mechanism so that I can apply the required test vectors in these pins also. So in case of embedded system based IP core testing, the main challenge is accessing these internal pins or internal IOs of the cores which are not accessible to the output world. Generally in a single, generally it's true for not only IP core, for any core based embedded system design, because there will be multiple cores, whether you manufacture or you get it from the IP vendor. In case of IP vendor, the problem is more higher because you do not have any control in the internal logic. Like for example, if you have all the 4 cores designed by you, then if required that I want to apply some test pattern over here, some test pattern over here, I can make some more adjustment. Maybe I can, if it is something, sometimes it happens that lot of test patterns are required to be applied to this pin, then I may try to make this as a input output pin. I can put this block here so that there is a direct input output connection. Maybe I can replace this block, so this IO pin here, I can do some kind of reorientation so that it becomes the input output ports are more available to the IO lines, that is external world IO. But it is not possible in the case of IP cores, because in case of IP cores everything is fixed, you cannot do much changes. So the problem will really happen if I have to apply lot of test patterns at this pin to test it. So testing of IP cores, the main issues, or IP cores or any core in that fashion in case of embedded system, the main problem arises how to access these internal pins and how to apply test patterns there. That is the main challenge. And in today's lecture we are going to look at it, that how can I access these internal points and how can I apply test patterns to that. Again repeating, this is the story with any embedded system core based design, because the cores are somewhat chips in itself, but they are not at the level of external devices which can be put on a breadboard or in a PCB. Rather this is a single silicon die, and basically you are putting all these at the fabrication level, so that these delays between these interconnects are much lower and you can have a higher frequency of operation for the entire embedded system hardware. So but problem happens is that the lack of observability and controllability, because these are the pins which lack observability and controllability. How to access those pins and apply test patterns is the main challenge for embedded system core based design, which we are going to look at in this lecture. So with this picture I have given you the motivation. Now basically technology advances allow embedded system hardware that earlier occupied 1 or more boards onto a single IC. So that means if you think of an entire system in previous days, there used to be multiple chips or even multiple boards connected to make a system. Okay, so but now basically the problem is that if you have multiple boards, size may be larger and all, it may be slower, low power, high power will be consumed, etc. So now what happens, basically we are putting multiple cores in a single silicon. So it leads to higher performance, low energy consumption and smaller weight and volume. So instead of multiple boards or single board with multiple chips, now it's a single die with multiple cores. So, but actually these codes are mainly heterogeneous. They can be digital, they can be memory, they can be of some other embedded kind of hardware, they can be analog circuits and so forth, and there can be also IP cores. So, basically different natures of cores will be placed on a single die and you have to test it. So, that is what is actually nowadays embedded system hardware cores are of heterogeneous nature. But again, I mean, we are only looking in these cores mainly at digital and memory chips. I mean, you can call it IP cores. Okay. So, IP cores are something like it can be digital, analog and even memories, but people will not tell you about the internal details. It is IP protected. Okay. So, different type of mixtures or different type of cores are possible. In this lecture mainly we will be focusing on, or in this course mainly your digital and basically your memories. But again, I want one type trying to say here that testing an IP core or testing that IC in separation have no problems, or they are very similar for the test pattern generation. Test pattern will tell you what to be applied and what you will get out as the golden response. Only when they are in multiple in a single core, multiple cores are put on a single die, the main problem is in accessing the test points. So, that is the main challenge of core based testing, which we are going to look at. Okay. So, in traditional system on board components where IC is designed, manufactured and tested by the same vendor, that was generally the case. In a very slightly 30-40 years down the line, generally what happened, there used to be a board and you used to manufacture some chips and you have to put on them. And sometimes if some of the chips were also from the other vendors, people used, as this was available as discrete elements, they could test it, and I mean and they could also guarantee to be its correctness by the vendor who is selling it. And then when you are putting in a board, if you require to test other chips also, you could put another discrete components. What I am trying to say here is that maybe this is a board, not this is a PCB. Right, and maybe we are having these 4 chips, because in a previous days it was chips, right. So, we had basically this is chip 1, chip 2 and 3 and 4 maybe we are purchasing from the other vendor. So, they are discrete components tested and put it. Maybe after that these interconnects may be difficult to test, because the chip point, basically the board's IOs are this way, right. But still you can make a probe here. It is more simpler to probe these lines and look at the values. That is possible. But it's slightly difficult, not as simple as the standard IOs, but still you can do it as a board. But in a die, if you think silicon, you cannot probe this. You require an external prober, and it's very difficult to break the chip and actually probe these lines. In a PCB, it is much simpler. Not only that, also you know that if I want to test this line, I have to actually make a multiplexing arrangement, because where I am applying something to this chip, data should not come from here. I have to give some external test data. So, that is possible. I have to put some multiplexing arrangement, like this is chip 3, I put some multiplexer, okay, and this is your chip, maybe this is your 2:1 multiplexer, this is your normal input, sorry, this is your test input, this is your normal input, and this is chip 1. So, I put a multiplexer, and normally this one will go, and the test mode external input can be given. So, I can easily put some kind of multiplexers and I can do it, because in the previous day I used to procure all these chips and put it in a board. So, wherever such type of difficult to observe and control lines were there, I can make a multiplexing arrangement. But in the die, sometimes it is very difficult to do, because there are a lot of other issues like loading of the pins, etc. Unnecessarily you want to, this is a big die like something there, you are putting some of the IP cores. There are some of the IP cores you are putting here. If I put some kind of multiplexing arrangements, so I mean and I do not know much details about these IP cores. So, and also in a chip, is inside a chip fabricating some extra basically multiplexers, etc. may not be that easy as it was done in a board, and also not very ad hoc. So, I should not say it's more difficult, because putting an extra multiplexer in a board as well as a die is now this silicon chip also is almost equivalent in difficulty level. But in the traditional level, when you are doing board based design, it was up to us that this pin is very important, I can put a external marks to go for test mode. These pins are not very important, I can take an ad hoc decision, because most of the chips are built by me, or few I have taken and I am soldering them in a PCB. But in case of a silicon or a die, it has to be manufactured, it has to be fabricated. So, I have to be very careful on what I am doing with the pins. So, there should be proper protocol of that manufacturing these devices. Or when in the case of a chip. To cut the long story short, in case of board based design, PCB based design, I can take much ad hoc decisions, because I was actually purchasing chips and manufacturing and doing a soldering, which is much more simpler than doing a fabrication. In fabrication, everything should be very much in a protocol or should be following a standard. So, core based embedded systems testing, to access those internal pins, there should be some kind of a standard, which allows a particular way of accessing these points or controlling these points. So that is one more important aspect we are going to look at in this lecture, that in core based embedded system testing, there what are the ways we can put some points in the internal of the interconnection of your cores and how we can access them. So in modern embedded system like NOC, SOC, components are basically cores. So cores can be soft core, firm core and hard core, as I was saying. So basically what is a soft core? Soft core means you purchase the RTL design. So in this case, it's a Verilog code given to you in the register transfer level. So slight modifications you can do based on your agreement with the vendor. There is something called firm code which is a net list. They will give you the gate level design. There also slight changes can be done, but of course you are not, it's something like an exe file is given to you. You do not know much about what exactly is the logic behind it, because the synthesized net list or gate level design is given to you. Many times you also purchase a hard layout, hardcore. That means only the full layout has been given to you. Very difficult to make any changes, because it is fully in the level of transistor design which is given to you. So generally full secrecy is one, they generally sell as hardcore. Firm cores and soft cores basically are more flexible, and you can very easily know what is the functionality of this cores. So they may be more costly to purchase, and because you can also do some kind of little bit changes, and there is no secrecy in those designs. So generally for most of the cases I will prefer to purchase a hardcore, because I do not want to invest much time on the other vendors' expertise. I will just take the hard codes, put them together. I will put those codes which I know how to design and build a complete system and sell it to the market. Also sometimes it happens that some of the vendors do not design anything. They basically take all the hard codes in the layout level, put them in a single die, make the interfaces and sell it as a product. So in that case, that company does not know the internal details about any of the codes. But with every core the test patterns will be given by the vendor. They say that if you apply them, the circuit will be tested, and then they do some kind of testing of the internal cores, and then they have to also test the interconnects, and as we will see more in this lecture. So the idea is that the cores with the test patterns are purchased, they are put onto the chips. Individual core testing functionality will be done by the test patterns given by the vendors. You have to now but only check the interface. You have to test it, because I have put the cores taken from the vendors, but I have to now check the validity of the interconnects and total integrity I have to validate, and then I can sell it to the market. So that is also in picture, that I may not be manufacturing any of the cores myself, only I am doing the integration, testing, integrated testing and selling it to the market. Maybe some IO I will design and do. So that way is the modern embedded system industry going on. So basically why it is large? Reuse, speeds up designs and bring external expertise. So basically what you can speeds up the design process. If I have to build all the designs myself, then it will take a long time to do it, and I will be selling my product to the market. So therefore what it does, you take different products from different company and put it together and sell it. So it's an external expertise. So the expertise for my company is not to build it, but rather integrate it. So therefore testing in embedded system core based design is a different challenge than what we have been looking at in the first few lectures, that test pattern generation, how to optimize that and so forth. Here the idea is integration and how to access those internal pins. So basically embedded system core user responsible for manufacturing and testing, that is I am the core user. So basically I am going to fabricate it. You have only given me the design at a soft level, that is basically at the netlist level or the RTL level, or basically at the gate level or even at the layout level. But I am going to put everything in a die and I am going to manufacture it. So see, basically I have purchased from you the GDS2 level, that is the layout level of the chip or the core, and also maybe at the RTL level. I am purchasing from several vendors, putting it to a single die in a design, sending it for manufacturing, and finally I have to get it from the vendor and I have to sell it on everybody's behalf. Then what I have to do, I have to take those code, manufacture it, test it. Test pattern somebody else will give it to me, means whoever has sold the codes will give it to me. But it's my job to test those individual codes as well as the integration which I have done. So the core user, that is basically saying that I am user, I am using all of your codes which you have given me, so it's my responsibility. However, this is not possible without the assistance of the core designer, because the core design is IP. So therefore you have just sold me a black box. I have to test the internals, but you are not going to tell me the internals. So what I can do, I have to take your help, and obviously as you have designed, you will not tell me the internal details, but you will at least tell me that apply these patterns boss and everything will be tested. So those things you will give it to me as the test patterns. So the core design assists by delivering predefined tests to the core. You will tell me that these are the patterns you apply. I assure that if you can apply these test patterns, you will getting 99.9% coverage, etc. for these fault models. But now the problem is, he is designing a core and he is saying that these are the pins you have to access and do it. But the problem is that now this will be in a bigger design. So maybe this will be coming into another chip like this, another block, and this may be your input outputs. Maybe these internal pins and these internal pins of these two cores cannot be available as output. So the test pattern or the core builder or the core who is designing of the core will tell you have to apply these patterns over here, and you have to probe these patterns over here, receive the response from these pins, and you are going to get the response analysis. But these are now become internal part of your main chip. So I have no access. So in case of embedded system design, as a core, as the manufacturer of the entire system, purchasing the cores from external people, it is my duty that how I can access these internal pins so that the entire system can be tested after manufacturing. So now the person who is actually designing or manufacturing these cores or embedded system entire design from the cores, it is his duty that how he can access those internal points. Again repeating, because embedded system core based testing means that is what is to be emphasized. That test pattern generation not problem, people are giving me the test patterns, I am putting them in a single die. My point is only how to access these lines and do it. As I told you, it's not a PCB based design, it's the chip is manufactured after putting all these cores. So there should be some kind of protocol and nice standard of how to access these internal pins and how to apply the test patterns and how to observe these responses, right? So the problem faced by the course design was how to apply these tests at the core boundaries. That is what is the problem. That some pins will become internal pins because the core vendor has sent you an entire core with input outputs, but some of the pins will be now internal pins of the core. How to access them? That is what is the challenge of core based testing. So again, this is what was our motivational example. Like for whoever has sold this core to me, he will tell you, see, these are the internal pins, you apply something, these are the external pins, somewhere you have to observe the response and analyze. Fine, but after it is becoming I have put it in a single die and manufactured it. So these are the pins which are no longer accessed from the external world. Maybe I can tell you that these are your external pins, these are your external pins, these are the external pins, these are the external. Problems are with this internal world. How to do that? How to access it? So again, very famous old story, scan chain is going to help you. So what is a scan chain? As you already know, scan chain means some of the flip-flops are made in a single shift register fashion, and whatever pattern you want to apply, you apply it and set it accordingly by the scan shift, and once the flip-flops have got those values, you can again go to the normal operating mode and test it and again capture the response in the scan chain, again bring them out. Simple idea is that maybe multiple points in the circuit has to get these values which are fed by the different flip-flop. So now what you have to do, say for example 0.1, then 0.2, like that, lot of points are over here, 0.3, these points are there, and these are all connected by D flip-flops. These are the D flip-flops and these are the D flip-flops, right? So in a scan chain, what we do, we put all these flip-flops in a chain in the test mode, and whatever value 1, 0, 1, whatever are required at this point, so we shift them by using a scan, using the scan mode, those values are applied and you get and you can do the test and again take back the response from the scan chain. Same philosophy has to be applied, or rather that is the natural way of doing it when I am going to access these pins. But in that case, the scan chain is not in the internal of the core, they are basically at the boundary points of all the core pins, as we call it the boundary scan. We actually call the word as a boundary scan. That means all these IOs, say maybe this is your one core and this is one some of the cores, right? So what we do is that along with the normal pin, we actually put a scan register, that is called boundary scan register. These are all the boundary scan registers. So basically, let me zoom it for you. So you can look at it. So it says, if you look at each thing, so basically these are the external IO lines, but here we actually put some extra logic which is called the boundary scan registers. They are nothing but flip-flops. So for example, if I want to access this point, what I can do is that I can shift the values in a scan mode and I can bring the value over here. Maybe I require a 1 over here, so you can start shifting the values to this point. I can easily access this. These points are not of a problem to give any values because they are directly connected to the input output lines. But for the internal one, I can actually apply a scan mode and I can bring in, and here simple same multiplexing arrangement like a scan register will be there. So you will decouple it and the value will be available over here. Same philosophy is applied, but actually we have to apply it in a scan mode, like a simple scan architecture. So this standard, as I told you, this is the core idea of doing a core based testing, and and there were different levels of standards that came up into picture. We started with 1149.1, then .9 which is for analog, and for embedded core test they call it the IEEE 5100 standard. It is proposed DFT based NOC test standard that facilitates embedded core and interconnect testing and test reuse. That is the core idea, that it will test the internal logic as well as the interconnection, because as I told you, the vendors will have sold it to you. With the internal logic to be tested, they will give you the test patterns. But it is my duty how I can test these internal lines, that internal connections, because I have taken them and I have integrated them. My job is to use the patterns given by you to test the internal logic, but this internal interconnects I have to do the test. So, like the way I scan chain, there is a protocol of designing scan chains. Similarly, if when I am doing at the boundary level or basically at the core level, so it is called the IEEE 1500 standard. So, basically the scalable, it contains source and sink for test stimuli and responses, which is called the source generator and analyzer. There is something called the text access mechanism, because there are multiple cores inside it and you have to target one core at a time when you are doing the internal test, and when you are doing interface test, multiple 2 cores may have to be taken into account. So, somehow you have to access the internal of the chip where a lot of cores are there. So, it is called the test access mechanism, and there is something called the wrapper, because the way you can directly access the IP core may not be all pins are directly given to you as the output in a flat nature for testing. If you look at, if you want to read more, you can find out that how you can know the internals of the chip by taking the scan out values. So, there are a lot of attacks which actually tends to know what is your IP design by scanning in the values of the scan chains. So, therefore, what people do is that they will put a wrapper, so that it, the test patterns can be applied and response can be obtained through a buffering. So, it allows the integrity of the IP core. So, the source and sink are generally AT. If it is a BIST, it will be internal hardware. If it is from the basically your external equipment, it can be through the source and sink are the AT, that so forth. So, source and sink means some pattern generator, which can be external or which can also be internal. The test access mechanisms, TAMs, are basically used to transfer the test vectors and response to and from the core respectively. That is, some internal connectivity has to be there, because if you look at it, in this case, the idea is something like, if I have to access, give some values over here, maybe this point is not directly available to me. So, therefore, there should be a text access mechanism. Like in this case, I can say this whole scan thing is basically a text access mechanism. So, for some of the important cores, I can give some dedicated lines, because maybe if these 2 pins are always accessed. So, to reduce the test latency, I can make this a direct input output by some kind of a logic. So, that means the way I am giving access to the internal pins of your core is called the text access mechanisms. Wrapper exists around each core to connect the TAMs to the core, as I told you that there should be some kind of a buffering to do it. A simple architecture, it shows that maybe I am going to test this under cut. So, this is the source and sink. Source and sink means this may be the AT, this is also the AT, this one. But this is the wrapper. Wrapper will actually tell the protocol how this text access mechanism or how the pins will be connected to the wrapper to test the core. And what is a TAM? TAM is basically how you connect the source and sink to the cut. So, as I have shown you, this boundary scan method can also be one way of having a TAM, is one way of accessing the test lines, right? It can also be something like, is a very highly critical part of the core which has to be tested. Many test patterns has to be given and recorded. So, I can put some kind of dedicated lines, input output lines for that. For all other these the others, I can put basically maybe a scan register, because testing by scan method will take long time. So, if more test time will be required. So, if less patterns can do the testing, so I can connect to a scan register. And but for the cut or for this IP block, maybe it's very lot of test patterns have to be there. It's a very critical block. So, I have to test it exhaustively. So, I can put a direct connection by wrapper to this, through the input and output. So, therefore, it is actually called the TAM. TAM means how you access the points. Source and sink means where you are generating the pattern and when you are receiving it. It can be an AT for an offline test. For a BIST, it can be the internal sources like test pattern generator or response analyzer can be put on the chip itself, which I think will have lot of full lectures are also available on built-in self-test down the line. But for the time being, you can just take the fact that for BIST means basically the test pattern generation and analyzer are put in the same on the same chip, rather than basically using a ATE to do that, right? And the wrapper. So, now we will basically try to look at, mainly we will try to look at these 2 parts in details, because the source, sink and source are nothing but some ways of generating the patterns. Generating the patterns means applying the patterns and analyzing the response. So, now important is test access mechanism, that how do you access the chips. So, it delivers test stimuli from the test source to the cut, transports the test response from the cut to the test and sink. That is the job. TAM design involves making a lot of trade-offs. As I told you, if you have a full scan based design, it will be very simple, low cost TAM, but the problem is that test time will be large, because you have to scan the values and bring it to the point to do the testing. So, so it depends, like, and also maybe I can have a serial TAM single line. So 1 by if 5 values has to be applied over here, it's a single bit, so you have to do it serially. If I have a parallel TAM, I can put lot of values directly, so it will be a faster way of handling. So you can easily understand this is a trade-off, speed and resource, speed of testing and the amount of resources used. Test time depending on the test transport capacity. So test data transport, like test data capacity, there is wider TAM, more number of IOs, as I told you, will have a higher access to the chip, and but resources will be more. TAM overhead means rises with transport capacity, lowering test time. So if you put lot of TAM resources, then basically lot of test patterns can be applied in parallel faster, but it will actually lower the test time. But the TAM DFT cost will basically be rising. So some people also think that if I have to go for at speed testing, very fast I have to test it, then actually you can also reduce this physical distance. Like for example, if it is a long line, why it is very important over here? Because single core and single chip and a chip with multiple cores means this area will be quite large. If this is a chip, these are all individual chips, then I can have a direct access and the test and the wire lengths are less. But in this case, as this if I have to directly access this TAM, then maybe the wire length will be higher, so leading to higher stray capacitance and resistance, and we cannot apply test patterns at a very higher speed. So if I can somehow put this on chip, so basically I can go for at speed testing, because you can just take, because they are full device physics, but the idea is very simple. If you have a very long wire length, so the capacitance and resistance will be higher, so you cannot put very high speed clock pulses there. But if I can put everything on chip, then this length of this will be lower, and basically you can do high speed testing. So we can put on chip sources and sinks, okay, and also that will make high speed testing. Also TAM can be shared among multiple cores, right? So basically that is some shared bus, okay, but actually it will reduce the wiring area, of course, but it will lead to reduced test concurrency. That means what is a shared bus. So single TAM, the bus, multiple chips are accessing it, multiple cores are accessing it, so you can access one core at a time. It's just the concept is very similar like a single bus and a multiple bus architecture. So the idea is very simple, that you can, if you are having more resources for the TAM is nothing but ways to connect to the different pins of the wrapper for testing the cores. So more resources, like more parallelism, more number of bit width you make for the TAMs. If you give more parallelism to that, your TAM overhead will be higher, but test time will be reduced. If you are using shared TAM, like shared bus, if you are using a serial TAM, actually the problem is that test time will be higher, but your overhead for the TAM is going to be lower. So again, the same thing I am showing you over here, embedded system containing 4 boundaries with boundary scan. So in this case, you can tell that it is a very simple one. I am giving the whole access by a scan. So in that case, that is my TAM, that I access each of these lines through a single scan chain. Or as I told you, you can also, if these are very important lines, so I can have 5 multiple input outputs where I can connect these lines. So this will be another TAM. For maybe it's not, maybe these 2 chips are not very important, sorry. Maybe these 2 chips are not very important. I am very thinking about these chips, so 1, 2, 3, 4, 5. I can connect these lines, and this will be say TAM for this logic. So I can have a direct parallel access to this. It will be more faster to apply the test pattern. Simple logic. So TAM means how basically you can access it, and higher will be the more weightage you put on the overhead. So basically means more we put in the TAM resources, test time will be lower. So that is actually the idea of a TAM. I will elaborate how it looks like. Basically it is nothing but simple scan register with slight modification, of course. So basically this is a wrapper. So this is the core. As I told you, as basically we are basically not having it's not a PCB kind of a design, so it's a chip which will be finally fabricated. So we should basically always try to follow a particular protocol of design, and it is basically IEEE 1500 standard. So the core, and of course as I am manufacturing a chip, I make it IP protected, I have to sell it. So and everybody will be connected through a single TAM mechanism and a very nice single standard architecture. So I have to maintain a protocol. So if I have a different wrapper, you have a different wrapper, he gives a different wrapper, and I have to put in a single core and try to test it together, it can be a problem. So therefore, while designing the chip with a wrapper, I have to know that there should be a particular standard of accessing all the core pins, so I have to follow the standard. So people also design a manufacture in that standard format. So it is very easy to put these chips, put it in a single die, and you can use the 1500 standard to access them, and you can easily, there should be no problem in handling the testing of different chips from different vendors. So you always maintain a standard. So basically we have, they said WPP, which is actually called the wrapper port. So this is the some ports which have parallel access. So WPI basically it is wrapper parallel in, parallel out, and parallel control. Control means basically means which of the pins you will want to, which of the lines you want to have in test mode, which pin you have to want to in functional mode, and so forth. This is just the controlling, just like controlling that which pin, like which kind, like control means what? Just like in a scan chain we have seen test mode, working mode. That is actually control. So this is parallel, wrapper parallel port is optional, is to speed up your testing requirements. So PI, WPI, WPU, this is parallel, wrapper parallel input, parallel output. Multiple pins you can apply to give the test patterns. Here the TAM will be of higher overhead because multiple patterns can be given. And there is a control. Control, as I told you, is when to go for test mode, when to go apply it for functional mode, etc. But this is must. Wrapper serial port is a must. That is wrapper serial input, wrapper serial output, and wrapper serial control. That is what is basically nothing. This one, this is a single line. So at least TAM should be of 1 bit. Otherwise you cannot do anything. So therefore this serial port is mandatory. That each of the pins in this core has to be accessed at least serially. Otherwise, if other testing cannot be done. So this port is mandatory. It is serial access. Each point will be accessed serially, and there should be a control. But if you want to speed up, you can also give parallel access. We will take more elaborate explanations which will be making it clear. So this is basically more elaboration on your on your core wrapper design. So this is your core. So there can be test inputs and test outputs. These are the parallel ones. That is again optional. But this is the functional inputs and functional outputs will be there. So sometimes what we do is that we generally it's a single, I mean this is inside the core, generally this is a single line they have shown in blocks, then it's multiplexed. Either you will give this or you will basically give this. So basically why I am saying this is optional, because then your TAM or test mechanism should also have parallel. It should be able to give multiple test vectors simultaneously. But anyway, let us assume that we have parallel access is provided. So basically, so these are two, and these are WBR is this is your boundary wrapper boundary register. This is like your scan. This is a multiplexing arrangement with a scan. I'll tell you. I'll show you this figure of this. Is something like this. So either the mode, the test data can go from here in this direction. This is the test data, and this is your input, normal input, and this is basically your output. So the output is going to the core. So this is testing. So if it's a single way of single mode application, if it is in that manner, then what is going to happen is that, and if I put another register over, this is another input to the core, and this is your input, another input line. So this is your scanning. So maybe I have to give a value of 1, 0 as the inputs to the core for testing. So as in a scan mode, so this one will be disabled. So this one will be disabled and this one will be disabled, test mode. So I apply a 1, apply a 0 as a boundary mode, it will come and apply to the core. But so this is a normal serial mode of doing, just like a scan. So you apply the scan, fill the scan chain, and after the scan chain has been applied, so you apply it and do the testing. But again, while normal mode of operation basically, so what is going to happen in normal mode of operation, this scan chain will not be enabled, so this one will not be enabled basically, and direct input will be going over here. So therefore there is a multiplexing arrangement in the boundary register. So either normal or parallel or normal mode. So test data can be going in this mode, right, and test data can be given out this mode, right. So this one I show, this one is erased. So this is a, this data can be given. It's a serial mode of doing it. But that is what is the idea. So I either configure these registers to go this is the functional mode, and in case of test mode, what I am going to do is if it's a serial mode, the values will be traveling in this one, and maybe I require a 1 over here, 0 over here. So this serial I will be applying, and this functional input will be cut in this manner basically, something like this, right. And then basically the output will also be appearing in this functional output, and it will be scanned out. Right, that is actually a serial way of doing it. And parallel, along with this, you can access, if the TAM has multiple parallel ports, so you can directly bypass these scan registers, and you can directly apply the test patterns. Maybe something like this. If I take this figure, it will be clear. So maybe, as I told you, so here I am putting all the values or probing all the values sequentially. But if I have some 5 parallel lines over here, so I can directly apply these 5 as the internal lines, direct values I can put, and I can do the test, apply the test patterns in a much faster manner. So that is actually, these things are corresponding to the parallel access, right. But serial is the simple one. So wrapper connects the TAM to the core and thus determines normal or test mode. One wrapper exists for each core and totally encapsulates the core. That is what is the idea. Okay, before I tell you, there are two very important registers. One register is called the WIR, which is the instruction register. That is what I am told you, that here the instruction is very simple, just how it's a decoder. So what it does, it tells when this has to be applied. So accordingly the multiplexing arrangement in the buffer boundary registers has to be changed, whether it wants to shift it or whether you want to access by this mechanism, whether I have to give this as output, whether I have to give this as output. So all these multiplexing arrangements for the boundary registers has to be modified, and for that there is something called the instruction register. So you give the values to the instruction register, and accordingly it will select in what mode the basically this buffer registers has to be in. There is something called a WBY, which is a bypass register. Why is a bypass register important? Because maybe I don't want to test this chip. Again, I will take this example, it will be clear. Why it is a bypass register and why it is required? Maybe I want to just access maybe this point, and maybe I want to access this point. So should I transfer these values in this manner and then come over here and apply it? Long time. So basically there is something called a bypass mode. In bypass mode what happens basically, so it is not shown over here. So bypass means the data will not flow over here, rather it will directly come over here. From here it will be coming over here. So basically from the bypass it will come over here. Bypass means it will not go around, there is a bypass way. So you do not, because I know that I do not have to test the chip, so it will be bypassed, it will be coming over here, it will be again coming over here, then again it is bypassed because I am not going to test it, it will again direct come over here, and then it will going to test this part. So bypass means I do not have to scan throughout this. So that is something called I can go around, instead of going around directly for the test pattern, I can directly send it out here. So this is called the bypass register. So it means if you have to scan through all the chips, all the cores in the die, it may take a long time to do that, and not required also at every point of time, because maybe only 2 cores I am interested. So some of the cores I will directly bypass. So instead of going in the roundabout direction, basically I will directly pass this chip. As I told you, not by this direction, I can go about by this. Okay, and then one more important thing I should say, that how to give the instructions etc. are actually in a serial mode, because already it is told that at least the serial mode of access to all the chip cores will be through the wrapper must be available. Parallel is optional, but sequential is must. So therefore all the instructions are given as a serial mode. The wrapper serial input output ports are serial interfaces to the wrapper. So this wrapper, basically this instruction whatever you are going to give, even if I want to give the values individually, this may not be available. So in this case the single bit transfer, so sometimes we will be giving the instructions, but it is in all serial mode. This also, of course, there can also be a what I say, you can also have, in some of the cases you can also have directly, you can access this instruction register in a parallel mode, but as I told you, in most of the designs by standard 1500, they try to keep this the instruction providing in a serial mode, because instructions are not very large in length, because instructions here are very simple control instructions. Instruction register in this case is just a decoder. So for one mode it will make the chip or registers go in this mode. In one mode it will be allowing it to go in this manner. In some of the instruction it will maybe allowing it to directly go by this bypass register. So it's just a decoder changing the multiplexing arrangements. So that's very simple digital design. So in this case the instruction register is nothing but a simple decoder, and the instruction lengths are also very less, because the instructions are very few. One more thing, I am not going into the very details of the protocol, because exactly what are the instructions, what are the name of the instructions, what is the input code for that will actually make the lecture very monotonous. So after looking at this basic architecture and the basic explanation I am going to give you, you can just go to the IEEE standard, I will give you the reference, you can read it. So it will tell you the exact code, what is the value of this instruction for this what is the instruction binary value for this instruction type, how the multiplexing arrangement changes, you can find out in the standard. But repeating it as you will take a long lecture, and it will make it very monotonous, because telling a standard is just like reading a newspaper without any without any kind of without, it's just a news means what I am trying to say is that standard means go to A, then go to B, then go to C. It's just like telling you what to do in a very clerical manner. But if you want to really write a 1500 standard wrapper, then of course you have to look at the standard and design. But in this 1 hour lecture, what I am trying to do is that basically I am trying to tell you what is the basic philosophy, so that after that you can easily go and read the standard, you can have a better appreciation of why the standard was designed like this, what are the facts etc. Right. So these are wrapper. So in this case, as I told you, this is the bypass register. So why this sequential input and sequential output, there is mandatory that if parallel interface is not there, still serial interface must be there. So you can apply the test pattern and you can observe the test pattern. Along with that, some instruction which I am going to give it to is also in a serial manner. As I told you, parallel access may not be given to you. So therefore by the standard they have called WIR, or the instruction are given in a serial mode. right. So what happens, WIR loads and executes this test instruction. So it will load it and it will execute. So instructions, I told you, the functionality is very simple, whether it may go around by this manner, whether you will allow this, or whether it will bypass this particular code is taken care of by this instruction register. WIR configures the operation of the wrapper according to the instructions shifted to it. That means the instruction is given in the serial form, and after the whole instruction is shifted, it takes the action. The WIR circuitry decodes the loaded instruction and provides the individual signals to buffer register, analyzer and data registers. A very simple idea. And as I told you, if you ask me how this cell looks like, so this is the scan input, scan output to the wrapper cell, boundary cell, or you can give it as a test input. This is input, normal cell functional input, cell functional output. That means it is something like this. It is going in and going out, and basically this is what is being scanned and going to scan output. So if you want to give a test pattern, it will be in this manner. If you want to give it to this is the core. If you want to shift some test patterns, this will be in this manner. If you want to give the test pattern, basically if it's an IO pin directly, like this pin, like this point, if you want to access something, you need not scan in the value here, you can directly give as the output. But if you want to give some test value as this pin, you have to scan in over here. So accordingly, you can easily appreciate that I can actually change this model. So if this is the input output pin, you can directly give the test pattern here, or you can also give directly the normal input output pattern over here. But if it has to be, if it is not an input output pin, maybe it is covered by some other core, then you have to scan in the value and you have to apply this. So simple standard multiplexing arrangement, as you can easily appreciate, there is some multiplexing arrangements to do it. And again, this, if you want to go to the next boundary scan value, boundary scan register, or they call it the wrapper boundary register. So it will be again, the scan will be passed over here. Same thing like a scan chain, only thing is that it is applied to the core boundaries rather than at the internal points of the chip. But as I told you, why they call it a standard? Because as I told you, multiple cores will be purchased from different vendors, they will have their wrappers, and I will put it and I have to go for test. So if everybody does not follow a standard and make their own wrappers, it is very difficult to do the boundary, the integrated testing. That is why we maintain a standard. Otherwise, it is very, very logical that we have to do it in this manner. But standard makes it very much fixed, and I know that if they are following 1500 standard, then this is the instruction, this is the bypass, etc., etc., etc. So very easily I can design my test integrity. So what are the very basic type of tests? Lot of tests are possible. One is called the bypass. Means what are different modes in which the boundary registers operate? First is called basically bypass. Bypass basically means wrapper allows functional modes. Basically the chip is working. If you can see, bypass. So in this case, what happens? Test patterns are traveling in this way. You can see the chip is working in the normal mode. So inputs are coming from the input output and basically is going to the output. This is normal functional inputs and functional output. That is, either the chip I am not interested in testing this core, or it can also be happening that basically this is operating in the normal mode. So these test patterns will come over here and go through the bypass register, it will come out. It will not be scanned, the distance, so the hop count is reduced. So it can be very, and what basically happens in this case, if you see the multiplexing arrangement, it will disable all the scan and direct connections will be made. So that basically changing of the multiplexer control will be taken care by of the instruction register decoder. Another very important is X test. So this is a functional mode. This is not actually a test. Sorry, this is a functional mode, not at all a test. Importantly, X test, because this is what I have purchased. This is what I have purchased. Now I have made this interconnections. How do I test it? Testing is very simple. You apply a 1, get a 1. Apply a 0, get a 0. That way, some pattern sensitive values can also be given like 1, 0, 1. Alternate, because that means there can be interference into the lines. You can also give something like 0, 1, 0, 1, alternate values, so that if they have a interference, both this can also be pulled, there can be a bridging fault between these two nets. So there is a lot of way of testing the interconnects, but the basic idea is that you send a 0, receive a 0, send a 1, 0, 1. You send a 0, will get a 0, send a 1, get a 1. Only that has to be verified. But sometimes, as I told you, sometimes you make different pattern combinations in the nearby neighboring lines, so that you can test for bridging faults or interference faults. Like one pattern can be something like I put a 1, 1, 1 here and a 0 over here, assuming the fourth line to be there. So in this case, all these ones can try to pull the 0 to a 1. That can also happen. But again, the test patterns are simple. You apply different combinations, but the analysis is very simple. You send a 1, expect it, this one, apply a 0 and this one. Whatever you send, you are going to just expect it at the output. And it is very well known. It is to be very well known by this test method or the model, that for testing it, what I should apply. Maybe just I can give you an example. Maybe I will first apply all 1, 1, 1, and it expects all 1. Then I will expect all zeros. Then I will get a 0, 0, 0. That's it. that is the stacked faults are tested. Maybe I want to see some kind of a bridging effect, then I will put 1 0 1 0 alternate and 0 1 0 this alternate. So both of these parties know that first it will give all zeros, then all ones, then basically alternate zeros, alternate 1 and I have to expect it at the output. So that is what is basically the predetermined test cases for the external lines. So in this case what you are going to do, it is actually called X test. So in this case you have to scan in the values of 1 1 1 1 and then actually this, like this, in this case it will actually block, it will all block these lines initially, it will actually get these lines over here and just do the XOR matching. So in this case this is called X test. So X test is one of the very important instructions which is given to test the internal connections. So it is means you can scan in the values, or if you have a parallel access given to it, if the parallel wrapper is given to it, so directly they can be fed over. There is the parallel access is given to you, then it will be faster. But as I told you, it's not a mandatory requirement to give parallel access. So sometimes it can happen that you have to do it in a normal serial mode. You can scan it over here, do it, and again scan the values at the output, and you can analyze the response. But if you have a direct scan out, direct parallel output, you can directly probe the value of the output and test it. This depends on the what speed and what overhead you give for the TAM. So here the TAM overhead will be very high because you have to give parallel access. But if you do not want a parallel access, that's also fine. You can take the values at the scan output and you do the test. So X test is very important. Testing the external pins. There is something called in test. In test means you have to test the core functionality. So in this case you can scan the values, required one you give, scan the values, required one you give, scan the value, required one you give. Then maybe 1 0 1 is to be applied for such testing of fault. Now who is giving you the test pattern? Very important point to note that I have purchased this core, I have no idea what is inside. The test vendor or who has manufactured the core will tell me that these are the patterns to be applied, then your in test is done. X test he will not tell anything. X test is my responsibility because I am applying something. X test is simple, I have to just test the interconnects, because if I know that cores are operating fine by the patterns the core vendor will give me, then it only remains that I have to test whether the internal lines are operating properly or not. Maybe I can do some kind of overall system functionality test, that is also possible, but that does not generally come under the P1500 standard. P1500 is very simple, you test your internal cores, you test the interconnects, more or less you are going to be done. So in test basically what happens, the vendor will tell me the points, so I will scan in the values, then again I will get the values at the output pins, and again I will scan out the values to the scan chain and analyze them. Right? So it's very simple. Again, if you are here, it will be a serial access. If you have a parallel port, then you can again directly apply these patterns over here, and you can get the output parallelly by the parallel TAM, and your job is done. Basically, this is what is called the, and this is very important, these are the references. Basically, this is the first one is the where you can read this whole standard document, and this also appeared in the Journal of Electronic Testing about this P1500 standard. So basically, with this we come to the end of this lecture. What we have seen over here, that is very important. We have not discussed P1500 standard line by line or the standard in a very protocol, in a very rigorous manner. Rather, what I have tried to give you, I have tried to tell you that what is the problem of embedded core based testing. Nowadays, most of the embedded systems are tested in the level of cores. You buy the cores, put in a single die, go and manufacture it. Now, you have to access these internal cores and basically test them. The problem is the internal pins, or because the core test vendor will tell you the input output test level of your core. They don't understand that whether this core will be put in the one corner or in the middle, or how much observability or controllability difficulty will be there. That the core vendor does not know. Therefore, he will put a wrapper and he will tell you that this is how my core can be accessed. Because the IP is an IP core, mainly people will not allow you to give all internal details about it. So they make a wrapper, and apart from that, the wrapper is also manufactured based on the 1500 standard, so that you can take multiple vendor cores and put it and test and try to access the cores in a normal simplified design protocol, because everybody is following the single standard. So you take multiple vendor cores because you know that all are following 1500 standard, you put it in the die and manufacture it. Now you have to access all the individual cores for the internal testing as well as the interconnect testing. Interconnect testing is, as I have told you, 2 cores will be there. You apply some values, binary values over there, look at the other end of the connection and you see whether the values are reaching over there or not. So that is also called an X test, which is definitely has to be supported by the P1500, but where you have to access the pins, where they will probe the values are all very clearly written in the X test instructions. But also again I have to do the internal test of the cores. In that case, again very important, the vectors are already told to you by the vendor that you apply it. Only problem is that how you apply that, because the core positions are not known a priori when you are designing the entire die. So therefore, you have to go by a scan method and you can put in this one. So therefore, this P1500 basically tells you how to access the chips and how to apply the test patterns and basically how to bring out the values and analyze it. So that tells a text access architecture. It's nothing to do with test pattern generation, how basically an optimize. It's not like that. It basically multiple cores are there. You make it a big die and put it there. How internally you access and test the lines and the internal. That is all about P1500 or core based testing. So core based testing is mainly how to get access to the internal points, observability and controllability. So this is one of the very important aspects which is coming out because more of the embedded system designs are core based. So therefore, in this because this module we are mainly talking about some of the interesting aspects of testing which are mainly emphasized for embedded system design. So in that respect, we were dealing in details with P1500 standard. With this, we come to the end of this lecture, and in the next lecture we will be seeing more issues on some type of important issues of hardware testing, mainly emphasized on embedded systems. Thank you.